Before we design or build a structure on the ground, we have to know what lies beneath the surface. To understand the soil conditions fully, we carry out a complete site investigation, which includes some in situ or field tests, collecting samples, followed by the laboratory tests on these samples. There are a few things we have to know. What is the soil profile? What are the soil properties? How deep is the water table? Are there any surprises? We drill boreholes for carrying out in situ tests and for collecting soil samples. We also dig trial pits up to about 4 meters in depth. Boreholes are expensive. Every additional meter of borehole costs money. We have to select the number of boreholes, their locations and depths wisely. Site investigation is carried out in 3 stages. Stage 1 is the desk study, where we try to get all possible information pertaining to the site, at negligible cost. This includes collecting existing maps and reports, and a site visit with a camera. Stage 2 is the mobilization of the drill rig, carrying out in situ tests, and collecting soil samples. Stage 3 is the laboratory tests on the samples collected from the field. The findings from the 3 stages are summarized in the site investigation report submitted to the client. Here is a drill rig at a riverbank in North Queensland, Australia, for taking samples from a borehole and for standard penetration tests discussed next. The photograph on the left shows a drill rig on a barge. The one on the right shows an in situ test truck with drill rig passing through some difficult terrain. The photograph shows a thin-walled Shelby tube sampler being pushed into a clay for obtaining a sample at shallow depth. For a good quality undisturbed sample, the area ratio has to be less than 10%. The photograph on the left shows 3 Shelby tubes, wrapped in plastic and the ends waxed, to preserve the samples and maintain the moisture content. The photograph on the right shows a thick-walled split-spoon sampler used with standard penetration tests. The wall is so thick, the area ratio exceeds 100% and the sample is very much disturbed. In all in situ tests, a probe is pushed or driven into the soil and the resistance is measured and correlated with the soil properties. The first 2 tests in the list, standard penetration test and static con penetration test, are the ones we use most of the time. In clays, we also do vein shear tests. Then there are dilatometer test, pressure meter test, and more. When planning a site investigation program, it is necessary to strike the balance between in situ and laboratory tests. There are parameters that can be determined by either of them. Both have their advantages and disadvantages. Standard penetration test, fondly known as SPT, works best in granular soils. A split-spoon sampler is driven into the ground, at the bottom of a borehole, by a 63.5 kg hammer dropped over a height of 760 mm. The number of blows required to drive the sampler by 300 mm into the ground is called the blow counter value, and denoted by N. In clays, excess pore water pressures develop, which can alter the effective stresses near the sampler and hence the N values are unreliable in cohesive soils. Work done or the energy imparted to the sampler per blow is the weight of the hammer W times the drop H. Since there are energy losses in the process, we multiply by the hammer efficiency. For the SPT rigs used worldwide, the hammer efficiencies vary in the range of 30% to 90%, making it difficult to compare the N values between 2 rigs. We can't compare apples and oranges. What we do is, We convert the end values from all SPT setups to 60% efficiency and call this value as N60. From now on, we will only use N60 in all our work. Hammer efficiency is inversely proportional to the blow count. Higher the efficiency, lower is the blow count. Therefore, just multiply the measured N by the hammer efficiency divided by 60 to get the N60. Even in a homogeneous sand with constant void ratio, the blow count increases with depth. The overburden pressure and hence the confining pressure increase with depth. No matter at what depth we measure N, we will standardize it to a reference overburden pressure of 1 atmospheric pressure, which is approximately equal to 1 bar equals 1 ton per square foot equals 1 kilogram per centimeter squared equals 100 kilopascals. We will call this as N1. If it is already adjusted for hammer efficiency, it is then N160. We multiply N by the overburden correction factor Cn to obtain N1. This N1 would be about the same at all depths in a homogeneous sand, reflecting the constant relative density. Here are several expressions used for the overburden correction factor Cn. Here, sigma VO' is the effective overburden pressure at the test depth, and Pa is the atmospheric pressure, which is 101.3 kilopascals. Out of these expressions, the ones suggested by Skimpton and Liao and Whitman, both from 1986, are quite popular. Here, we have plotted the overburden correction factor Cn against the normalized effective overburden pressure, which is a measure of depth. When sigma VO' is greater than half Pa, which is about 2.5 meters depth or 50 kilopascals overburden pressure, all the expressions are in good agreement. There is significant spread at very shallow depths less than 2 meters. For the standard penetration test, we also apply corrections for borehole diameter, including liners within the sampler, and shallow boreholes. Most of the time, these corrections can be taken as one, leaving us only with the efficiency correction. In dense sands below water table, driving the sampler makes the sand dilate and induce negative excess pore water pressures which temporarily increase the effective stresses. This would lead to overestimation of the N value. Terzaghi and Peck suggested a correction for this phenomenon. Here, you can see a schematic diagram on the left and a photograph on the right of an SPT setup. We simply raise the 63.5 kilograms hammer by 760 millimeters and drop on the drill rod attached to the sampler at the bottom of the borehole. The number of blows required for 300 mm penetration is the blow count or AN value. These are measured at 1 to 1.5 meters depth intervals. Blow counts are usually measured for 3 subsequent 150 mm penetrations and the first set is ignored. Here are the schematic diagrams of a donut hammer and a safety hammer. You can see clearly why a safety hammer is safer than a donut hammer. The top photograph shows a complete split spoon sampler used in a standard penetration test. The bottom photograph shows the same sampler dismantled, showing the driving shoe, the longitudinally split sampler, and the coupling head that connects the sampler to the drill rod. When we do an SPT at a certain depth, we get an N value. From that, we can compute N1, N60, and N160. Always check what N we are referring to. We generally use N60 and N160 in the analysis and empirical correlations. In granular soils, we can estimate relative density, friction angle, and Young's modulus. We can also estimate the equivalent con resistance from a con penetration test discussed next. SPT is unreliable in cohesive soils. However, the relationship shown here can be used to estimate the undrained shear strength of the clay. As before, Pa is the atmospheric pressure, which is 101.3 kilopascals. These are real data to show that no matter what the hammer efficiency is, N60 values are the same at a specific depth. In a static con penetration test, a 60-degree con is pushed into the ground at a steady rate of 2 cm per second. The resistance at the con tip QC and the sleeve Fs are measured separately. In addition, the pore water pressure is also measured at one of the 3 possible locations shown here. The 3 measurements are taken at very short depth intervals, making them almost continuous. Cones with pore water pressure measurement facilities are called piezo cones. At any depth, the friction ratio is defined as the ratio of Fs on QC, expressed as a percentage. This varies in the range of 0 to 10%, with lower end of the range for granular soils and upper end for cohesive soils. This is called the soil behavior type or SBT chart. This is a con resistance versus the friction ratio plot with 9 different zones. Depending on where we are on the plot at a specific depth, we can identify the soil type. Here is a typical log from a piezo cone test, showing the variations of the con resistance, friction ratio, and the pore water pressure, with depth. Note that the readings are almost continuous with depth. In granular soils, we don't always have the luxury of having both SPT and CPT. If we have N, it is desirable to be able to estimate the corresponding QC, and the other way around. We use this graph to go between the two AN and QC. Berland and Burbage, and Robertson et al. Suggest a range lower and upper bounds. Calhoy and Main, and the Canadian Foundation Engineering Manual also give their suggestions, which are quite popular. The ratio QC on N60 increases with the median grain size. Vein shear test is for clays, especially for medium to soft clays. It measures undrained shear strength of the clay. A vein, consisting of 2 perpendicular rectangular blades, is pushed into the clay and rotated at the rate of 0.1 degree per second. From the torque required for the rotation, the undrained shear strength is determined. In 1972, Beerim observed that the undrained shear strength is overestimated by the vein shear test and proposed a correction factor to multiply. Here is a mini vein used on the laboratory samples. Pocket penetrometer to a geotechnical engineer is like a stethoscope to a doctor. It is a small device like a pen that can be carried in pocket. It is mainly for clay soils. The spring-loaded stem is pushed into the walls of an excavation of a specimen and the unconfined compression is read off the scale. The test costs nothing, but the estimate of the unconfined compressive strength is also pretty rough. You will see tens of these in a site investigation report summarizing the soil data from a site. There would be separate bore logs for each borehole and trial pit, covering the entire depths, and some extending to more than 1 page. There are many reasons for instrumenting a structure or facility at a site. We use a range of geotechnical instruments for measuring the different parameters. The book by John Dunnicliffe is an excellent reference on this subject. Settlement plates are simple devices with a flat base and a stem embedded in the soil. The elevation of the top of the stem is monitored with time and the settlements are determined. Piezometers are used to measure the pore water pressures. What you see on the left is a vibrating wire piezometer. On the right, you can see the components of an inclinometer. The long inclinometer casing can be installed vertically or horizontally to detect the horizontal or vertical deformations, respectively. Site investigation program includes in situ testing, sampling, and laboratory testing. SPT and CPT are the most popular in situ tests. SPT is mainly for granular soils. CPT works in all soils. Van shear test is good in medium to soft clays for determining undrained shear strength. Geotechnical instrumentation is to monitor the ongoing performance, when there is a need.